you must not have your mic, your walkie-talkie on.
No, it's on.
Can you hear me?
No.
Can you hear me now?
Sorry, it was off.
Please ask everyone to sit down. I will turn your microphone.
Okay, places everybody. Camera, sound. I now call to order the lecture portion of the Society's 2530th meeting in what is now the 154th year since its founding on March 13th, 1871. Good evening, everyone. My name is Larry Milstein. I'm the president of PSW, one of the oldest scientific societies of Washington, D.C., committed to providing a forum to further scientific understanding and inquiry. Welcome to our members, guests, and friends to the lecture portion of today's PSW meeting and to the lecture by Stephen Eckel on measuring the emptiness of ultra-high vacuums. A special welcome to newcomers here and online, coming in for the first time, especially any PSW meetup members who met for PSW's first pre-lecture get-together at a local hangout with PSW member at large, Ellie Wonder. Thank you, Ellie. Let's thank our sponsors for tonight. Society is grateful to PSW full-year sponsors, PSW member Mike Helton and Helton Associates. Thank you, Mike. And PSW member Joe Schulman and the Schulman Foundation. He's not here, but thank you, Joe. And to the sponsor of tonight's lecture, PSW member Charles Clark. Thank you, Charles. The Society needs your support. Believe it or not, it takes money to post these things. So if you're not giving and feel you can give more than you have, please don't hesitate to donate. I'm pleased to announce that members gave more than enough to fully fund the generous matching grant. Overall, a $15,000 benefit to the Society. So thank you to all of those who gave, and especially thanks to the match donor for his remarkable generosity to PSW. Now I'm pleased to announce the following new members. Michael Hogston, Chief Medical Officer retired from OSHA, interested in environmental and occupational medicine and comparative regulatory philosophy. I learned a PSW from a member. Shrestha Obla, a robotics software engineer with Anduril Industries, interested in robotics, hardware engineering, aviation, astronomy, and evolution, who learned of PSW from a Google search. And tonight's speaker, Stephen Eckel, who learned of PSW from our invitation to him to speak here tonight, and whose interest will be clear to you in part from his lecture. All members are entitled to a signed copy of Compendium Volume 17 of the Bulletin of the PSW. If you haven't received yours and you're a new member, please come see me after the meeting. All members are invited to pre-lecture receptions and dinners with the speakers for camaraderie and interesting discussion. If you are interested in membership, you can access a membership application on the PSW website by clicking the blue Join button on the home page at the upper right-hand corner. If you're here in the Powell Auditorium and you're interested, you can access the application using the QR code on the business cards on the tables at the back of the room. PSW Science membership is open to everyone with a genuine interest in science and in the free exchange of scientific information, informed discussion on scientific subjects, and the promotion of scientific inquiry. Recording Secretary Scott Matthews will now present the minutes of the 2,529th meeting and the lecture by Gordon Guyot on evidence-based medicine and the grade framework. Scott.
Thank you, Larry. Good evening. On January 23rd, 2026, members of the Society and guests joined the speaker for a reception and dinner at 5:45 p.m. in the members' dining room at the Cosmos Club. Thereafter, they joined other attendees in the Powell Auditorium for the lecture proceedings. In the Powell Auditorium of the Cosmos Club in Washington, D.C., President Larry Milstein called the lecture portion of the 2,529th meeting of the Society to order at 8:06 p.m. Eastern Time. He began by welcoming attendees, thanking sponsors for their support, and announcing new members, and inviting guests to join the Society. Scott Matthews then read the minutes of the previous meeting, which included the lecture by Bernard Carlson titled Tesla, Marconi, and the Invention of Radio. The minutes were approved as read. President Milstein then introduced the speaker for the evening, Gordon Guyot of McMaster University. His lecture was titled Evidence-Based Medicine and the Grade Framework. The speaker began by discussing EBM, or evidence-based medicine, saying that while it has changed the world, there is more work to be done. He described medical treatment before EBM as largely based on physiological rationale, clinical experience, and expert recommendation. He claimed that the first paper published on evidence-based medicine appeared in 1991 in the American College of Physicians Journal Club. He presented the original, quote, hierarchy of evidence for therapy. In order of importance were randomized trials, observational studies, basic research, and clinical experience. He discussed the Cochrane Collaboration, a British organization that performs systematic reviews and meta-analysis of published medical studies. Guyot presented an example of the importance of such systematic analysis by discussing a 1990 study on thrombolytic therapy. The study enrolled 40,000 patients, only 20,000 of which received the therapy, at least 10 years after the evidence demonstrated efficacy, meaning that 20,000 patients were denied an effective treatment because the statistics had not been evaluated. The speaker discussed the use of lidocaine in treating myocardial infarction, a common practice in the 1960s and 70s. He claimed that meta-analysis performed in 1989 clearly showed no benefit and likely showed harm. The speaker made the statement, quote, evidence does not make decisions, people do, end quote. To demonstrate this principle, he conducted a poll of the audience, describing the risks and benefits associated with a particular treatment and asking how many adverse events they would tolerate per 100 patients. A small number of people indicated that they would tolerate a small number of adverse events, while the majority of the audience said that they would tolerate more than 20, clearly demonstrating a wide range of opinions with respect to the risk-benefit analysis. Guyot showed actual data from both physicians and patients, again indicating a wide range of acceptable adverse events. Above 20 adverse events per 100 treatments, patients were 5 times more likely to accept the risk than physicians. The speaker said that physicians should not substitute their values and preferences for those of the patient. Guyot summarized the 3 principles of evidence-based medicine as follows. Some evidence is more trustworthy than other evidence. Good clinical care requires systematic summaries of the best available evidence. Evidence by itself is never sufficient. The speaker provided a history of the publications on EBM in medical journals, the first paper in 1991, a second paper in 1992, a user's guide in 1993, and a 25-part series published in JAMA, Journal of the American Medical Association, completed in 2000. The third edition of the user's guides, in both long form and short summary, were published in 2015. Guyot said that EBM has become a, quote, core competency in medicine, nursing, and rehab science. He said that by 2007, medical schools had to teach EBM in order to be accredited, and that it was widely considered to be one of the top 10 most important advances in medicine since 1840. Guyette then discussed some of the shortcomings and misgivings of EBM. He said that in the 1990s, he assumed that all medical students, upon completion of their residency, would be able to assess and critically appraise the methods and results of journal publications. He said that this was very unrealistic and found that very few could. By the early 2000s, he and others in the EBM community concluded that not all practitioners need to appraise evidence, quote, from scratch. The speaker described the grade system, grading of recommendations, assessment, development, and evaluation, a transparent, structured framework used in healthcare to rate the quality of scientific evidence and determine the strength of clinical recommendations. Guyette described what was required to make grade, quote, irresistible to clinicians, patients, and developers. This included introducing rapid recommendations, creating an electronic platform, creating decision aids, and implementing platform trials with rapid meta-analysis. He described how GRADE and EBM performed during the COVID pandemic, saying that it produced unprecedented rapid production of evidence and rapid meta-analysis, leading to 6 classes of drugs and several vaccines within 2 years of the outbreak. The speaker ended his talk by saying that there is now widespread recognition of the need for hard evidence, the standardization of evaluation metrics, and the systematic review and meta-analysis of that evidence, but that more work needs to be done in educating clinicians to evaluate research and in the application of shared decision-making. The lecture was followed by a question and answer session. A member asked Guyette if he has seen a generational shift with younger practitioners being more able and willing to accept the suggested changes in methodology. Guyette responded, quote, "The answer is yes, and it has been fairly dramatic," end quote. He said that in the beginning there was an intense resistance and that widespread acceptance was at least partially due to older physicians retiring and being replaced by the next generation. A member asked, quote, "Is it wise to disregard physiological rationale?" End quote. Guyette responded that EBM and GRADE do not suggest ignoring physiology, but they require randomized trials to verify the efficacy of any treatment, regardless of the rationale that motivates that treatment. A member asked both about the risk of data overload and, quote, bad actors or misinformation. Guyette responded that rapid meta-analysis has become so efficient that it is unlikely that we will, quote, drown in data. He said that he had the sense that the EBM community did not have good strategies for dealing with misinformation, but that he had no real evidence to support that conclusion. A member on the live stream asked if people in the EBM field were aware of Dr. Ignaz Semmelweis, who proposed many of the ideas of evidence-based medicine 160 years ago and was then committed to a mental institution. Guyette said that it was a very famous story. He described how the vitriol Semmelweis experienced reminded him of the reaction of so many doctors in the early days of EBM. He said, quote, "Fortunately, insanity did not set in my case," end quote. After the question and answer period, President Milstein thanked the speaker and presented him with a PSW rosette, a signed copy of the announcement of his talk, and a signed copy of Volume 17 of the PSW Bulletin. He then announced speakers of upcoming lectures and made a number of housekeeping announcements. He adjourned the 2529th meeting of the Society at 10:06 p.m. Eastern Time. Temperature in Washington, D.C., minus 2.8 degrees Celsius. Weather, mostly cloudy and windy. Dinner attendance, 49. Lecture attendance, in person, 58. Live stream, 16. For a total of 74 viewers. Views of the video in the first 2 weeks, 144. Respectfully submitted, Scott Matthews, Recording Secretary.
Thank you, Scott. Are there any comments on the minutes? Corrections, questions? Hearing none, I will accept a motion to accept the minutes as read. Thank you, Bob. Have a second. All members in favor? All members opposed? Minutes are accepted as read. Will be posted to the website in due course. We now turn to tonight's lecture by Stephen Eckel. Steve is group leader of the Fundamental Thermodynamics group at the National Institutes of Standards and Technology, fondly known as NIST. Previously he served as research physicist at NIST, developing quantum-based cold atom measurement standards. His research centers on cold atom sensing and precision measurement, particularly the use of atoms and molecules to create calibration-free sensors for pressure, vacuum, and temperature. A major focus of his work is translating quantum systems into practical metrology tools that can function as primary standards and deployable instruments. Steve was a member of the team that developed the cold atom vacuum standard, currently the only primary standard of vacuum pressure in the ultra-high and extreme high vacuum regimes. And he and collaborators demonstrated the portable cold atom vacuum standard, a first-of-its-kind absolute vacuum standard in quantum mechanical vacuum pressure sensors. He's an author on numerous technical publications and an inventor in 6 patents. Among other honors and awards, he is the recipient of the Presidential Early Career Award for Scientists and Engineers, a Department of Commerce Bronze Medal for the PCAVS demonstration, and the Physical Measurement Laboratory's Scientific Leadership Award. He earned a BS in physics at Lehigh University and a PhD in physics at Yale. All questions will be fielded after the lecture during the Q&A session. Steve, the stage is yours.
Excellent. Thank you very much, Larry. And thank you all for coming tonight. It's a privilege and an honor to be here and deliver this lecture, which I have kind of been pondering over the last few days. I want to make sure that I give you enough technical detail, but I also explain it as clearly as I possibly can. So if some of you come away and you feel that I've left something out, please speak up during the question and answers period. If some of you feel like it's gone over your heads, also speak up during the question and answer period, and I will try to explain it better. But what I'm going to tell you about today is our work at NIST to develop new vacuum standards. And as Larry said, I'm currently the group leader of the Fundamental Thermodynamic Metrology group. So before I get deep into my lecture, I thought I would take a moment to at least perhaps suggest a reason why I, and therefore you, are here tonight listening to me. And I think it may have something to do with this. This is a 1908 Stanley steam car. So this is a car which is powered by steam, just like a steam locomotive in the 1800s. In fact, the engine, the steam engine, is down here in this copper case. And you can see me, I'm up here pushing on this front tire with my father, who's just out of sight there, while my brother here is fiddling with something in the driver's seat, probably the throttle. And to be honest, I don't know why I'm sitting here and it looks like I'm pushing this car. I swear this car moves under its own power most of the time. But here, clearly something's gone wrong, so I'm pushing it. And this is just one of the many things that I had done with this car over my entire life. My family's owned Stanley steam cars since my great-grandfather, and so I grew up working on these devices. If you know anything about the history of steam engines, they are responsible mainly for the invention of thermodynamics in physics. And so I think you may have different philosophies about how one's career evolves. Maybe you think that your career is kind of like a random walk where you pursue different opportunities that come up at different times. Or maybe you think that you're destined to pursue a particular path. But no matter what your philosophy might be, you have to say that it's kind of unique that I, who worked on these cars as a little kid, ended up as the head of the Fundamental Thermodynamic Metrology group at NIST. Now, I also bring up this car because it actually can tell us something important about measurement by looking back at the history of the automobile industry in this country in the early 20th century. So as I said, this car was manufactured in 1908. And in 1908, there were lots of different car companies, car company trying to find a competitive edge. Stanley Steam Cars thought they had a competitive edge because they operated on a tried and true technology, steam engines. Everybody knew what locomotives were, and so it was a very tried and true technology. They thought internal combustion engines were dangerous. They, in fact, labeled them internal explosion engines to make them even sound more dangerous. But that edge didn't really pan out, as we all know, because we all drive internal combustion or now electric vehicles. This company was also coming up at around the same time. This is a Cadillac. Cadillac in 1908 was a luxury car manufacturer. And in 1908, Cadillac had already achieved a marvelous engineering feat, which they actually kind of kept a secret until one of their representatives in England decided that they needed to have a public display to show it off. And what did this person do? Well, they organized that 3 of these Cadillacs, this is a 1908 Cadillac, it could have been Cadillacs that were very similar to this, I don't know the exact model, but they brought 3 of them out to a racetrack outside of London. And they took them apart in the full view of the public, all 721 components of these Cadillacs. They then took all of these parts, and they mixed them up, and then reassembled 3 cars out of the parts. Now, amusingly enough, the cars all had different color paint when they started, so the mismatched paint on the 3 reassembled cars really drove home the point that these were actually assembled from various parts. Now, when they finished reassembling it, came the moment of truth. They tried to turn them on. And so at the time you would crank the front of the car had a crank, you'd have to crank it in order to turn over the engine. The first 2 turned over on the first crank. The third required only 2 cranks, but it turned over. And then they proceeded to drive these 3 reassembled cars around the raceway for a total of 500 miles. Now, this doesn't sound like much to us today, but what they had demonstrated on that racetrack in 1908 outside of London was the idea of interchangeable parts, something that we just take for granted today, that we could just take apart from this assembly and move it over to this assembly and it'll work just fine. But this was astonishing in the 1900s because if you owned a car or you owned a wagon, there was always some components on there that didn't fit other cars and wagons. It was custom to that car, custom to that wagon. And the way Cadillac overcame this and invented interchangeable parts was they solved a measurement problem. So Henry Leland was the CEO of Cadillac, the first CEO of Cadillac, and he imported the first set of what are called gauge blocks. That's these things here. Gauge blocks were invented by a gentleman named Carl Johansson in Sweden in the late 1800s. And what these are literally blocks of metal that are machined and polished to a very exacting length, fractions of a thousandth of an inch. And they're so polished, in fact, that you can take them, stick them together, and ring them together so that they form an even larger block. And using a set of these, you can make almost any length that you wanted with an astounding amount of accuracy. Henry Leland bought the very first gauge block set that Carl Johansson made in English and imported it into the United States. And he used this in his machine shops at Cadillac to achieve an unprecedented level of accuracy in machining. He used measurement to improve his machining process to make interchangeable parts for his cars. Measurement, in this particular case, led the way, because Carl Johansson actually invented the gauge block before Henry Leland used it. And so sometimes we have to go out and we have to solve potential measurement problems in order to drive innovation. Now, you may say, but Cadillac didn't really take advantage of it. That was Ford, right? Ford took interchangeable parts and made the Model T. Did he go out and buy a bunch of gauge blocks from Carl Johansson? Well, not exactly. He actually just bought Carl Johansson. He gave him a very handsome salary and moved him from Sweden to Detroit and set him up shop in Ford. And together they made gauge blocks for probably the next 20 years that had both Ford and Johansson's name on them. So that's yesteryear. But it has, I think, lessons for us today. This is the modern milling machine. This is the modern machine shop of today. For those of you who don't recognize what this machine is, this is what's called an extreme ultraviolet lithography machine. All of the most advanced chips that drive the AI revolution, all the advanced chips that are in your phones or in your computers, are nowadays made in machines like this. And the heart of this machine is EUV light, extreme ultraviolet light, light at about, if I remember correctly, 18.1 nanometers. And this light is shined on from a source off of various reflected optics all the way down onto a silicon wafer to pattern the circuitry for these chips. And it's very important when you're operating one of these machines to have measurement involved. Because there are not just length measurements, but there are light measurements that you have to do in order to make sure the machine is working properly. And one of the most important measurements is actually vacuum. Because if you were to try to do this process in air, all the air molecules, the water, the oxygen, and the nitrogen, will just scatter away the 18.1 nanometer light in distances that are like a centimeter. And so the light will never go very far. So you need to make a very pure vacuum in order to get the light to propagate far enough from the source all the way to the wafer where the chip is being patterned. This is not the only place today that you can find really pure vacuums. These are two very exquisite machines that have been built over the last 2 to 3 decades. These are the Laser Interferometric Gravitational Wave Observatories, or LIGO. There's 2 of them, one in Livingston, Louisiana, and one in Hanford, Washington. And these are large laser interferometers. So these arms, they have 2 perpendicular arms, which are kilometers in length. And there's a laser in the main building here, which gets split and sent down these 2 arms. And then it hits a mirror on the far side, and the laser comes back, gets recombined, and when it gets recombined, whether or not it forms a bright or a dark fringe is dependent on the difference in the length of the 2 arms. And you can use these machines to do some pretty impressive things, like, for example, detect the merger of 2 black holes very, very far from Earth. And so from the LIGO collaboration's original paper in 2016, this is the data of them simultaneously detecting 2 identical signals, despite the fact that these detectors are many thousands of kilometers apart. And these are indeed the merger of 2 black holes. But again, this happens inside a vacuum. That light that goes down these arms can't be scattered, can't be shifted by the air molecules that you would find if you were to try to do this in atmosphere. And so there's actually a very large, essentially vacuum tube that the light travels down that has been evacuated to ultra-high vacuum pressures. So how do we quantify vacuum? I've tried to convince you that there's at least vacuums out there that are important, and I've said that they need to be very pure. But how do we quantify that? Well, I work at the National Institute of Standards and Technology, and our mission is to disseminate the System International, or the SI system of units. The SI system of units since 2019 is defined by 7 base units: the kilogram, the meter, the second, the amp, the Kelvin, the mole, and the candela. And these are all actually defined based on fundamental constants of nature. Now, you don't see pressure in this SI system. You have to take several units and combine them together to get pressure. So if you remember, pressure is force per unit area is the traditional definition. And so we have to take the units of force, which are kilograms, meters, and seconds, and we have to combine those with area, which is also meters. And so the traditional way of getting at a pressure is kilograms, let me think if I can get this right on the stage, kilograms per second squared per meter. Is that right? I don't know if I did all the exponentiation correctly on the stage. But in any event, this leads to a derived unit called the Pascal. So what is a Pascal? It's 1 Newton per meter squared, and a Newton is a kilogram meter per second squared. So just to kind of give you a sense of scale for what it means to, what the Pascal is, I'm going to put up on the screen here a number line. This number line is a logarithmic number line, so each tick here represents a factor of 10. And let's start right here at the center, 10 to the 0, that's 1 Pascal. So what is 1 Pascal? What is 1 Newton per meter squared? Well, if you sit down and you calculate it, it's actually the amount of pressure that's exerted by a dollar bill if you were to lay it flat on a table in Earth's gravitational field. So it's not a very large amount of pressure. That's a pretty weak force. It's a pretty weak pressure. And in fact, atmospheric pressure is many orders of magnitude above that. It's up here at 10 to the 5 Pascal, or 100 kilopascal. That's what we consider atmospheric pressure. Everything underneath 100 kilopascal is generally considered to be vacuum. And we vacuum metrologists have divided this up into 5 different vacuum regions. We've got, starting just below atmospheric pressure, we've got low vacuum. As we increase the vacuum level, we go to medium vacuum, high vacuum, and then as pumps and systems and engineering improved, they needed to grab ever more fantastic adjectives. And so from high vacuum, we go to ultra high vacuum. And then from ultra high vacuum, we go to extreme high vacuum. But this brings us down from 10 to the 5 pascals all the way down to about 10 to the minus 12 pascals. Now, where can you find these pressures in the natural world? Well, if you went to the top of Mount Everest, you would get down to about 30 or so kilopascals, so you'd reduce down from atmospheric pressure by about a factor of 3. If you go out to Mars, Mars has a much more tenuous atmosphere than Earth because it has no magnetic field to protect it from the dangers of space. And so its atmosphere is actually more like a few hundred Pascal. If you've ever seen vacuum tubes glow in good traditionalist audiophile amplifiers, those vacuum tubes are operating in high vacuum regimes, usually somewhere around 10 to the minus 5 to 10 to the minus 4 Pascal. And people often think about space as a vacuum, but even space still has some particles left over in it. And so if you go up to where the International Space Station is in low Earth orbit, you're only actually getting down to about 10 to the minus 7 Pascal. You're only in the ultra-high vacuum range. And I can make much better vacuums than that here on Earth. Go out to the moon, you're getting very, very far away from Earth, but there's still some effects from the moon's outgassing into space. And there the pressures are more like 10 to the minus 10, 10 to the minus 11 Pascal. But if you really want to get really, really low, you have to go to find those voids in between stars. There you can get down to maybe 10 to the minus 15 Pascal. That's the probably lowest you can go in the natural world. But the best vacuum that you can make is also worth something. All of these vacuum levels are important for modern commerce. So aerospace operates in this regime starting from atmospheric pressure down a couple orders of magnitude. And the aerospace industry is interested in this because it's basically the way that they determine altitude. Your plane, when you're flying from point A to point B, doesn't determine your altitude using GPS. It determines its altitude using pressure. And planes actually fly on isobars. So the ability for you to measure your altitude properly and avoid a collision with another plane is dependent on how well you can measure pressure. We don't necessarily think about it, but every time you open a jar, you hear that popping sound of the vacuum breaking. Food safety is actually very important for vacuum is very important for food safety. I mentioned the most elaborate chips are made in the highest vacuums, but there's all sorts of semiconductor chips and nanotechnologies that are made in vacuums that aren't as pure as that. Mass majority of semiconductors are made in kind of the medium vacuum to high vacuum regime. And then I've mentioned EUV lithography already, so I won't go back into detail again. Big science experiments like accelerators also operate down here in the ultra-high vacuum. And we're seeing a lot of emerging quantum technologies. Now, quantum technologies expand all sorts of pressures and temperatures, but there's a lot of now very interesting quantum computing platforms that operate in the extreme high vacuum and below. And so this is a picture of 2 ions that are in an ion trap in one of these extreme high vacuum environments. If it wasn't in that extreme high vacuum environment, it would suffer collisions with molecules that are left over inside their vacuum chamber. Those collisions would dephase the quantum information that is stored in these ions and ruin your quantum computer. And this regime also lets us study unique states of matter. So this picture here I actually took as a postdoc when I was at NIST. And it's actually a special state of matter called a Bose-Einstein condensate, which is basically take a collection of bosonic atoms, laser cool them, and evaporatively cool them to achieve quantum degeneracy. And then at the time, I was able to shape them in any shape that I wanted, at least two-dimensionally. So I turned them into the logo of the joint institute of which I was a part between NIST and the University of Maryland, called the Joint Quantum Institute. So how do we measure pressure? I've now tried to convince you that pressure is very valuable to us in the modern economy. How do we actually measure it? Well, we're trying to undergo a revolution in how we measure it at NIST. I've already alluded to the classical definition of pressure, which is force per unit area. And so under this condition, if you think about a gas and how it exerts pressure, a gas is made up of molecules and atoms. They're all flying around with some kinetic energy. They bounce off of walls, exert a pressure, because as they bounce off the wall, they exert a momentum kick on the wall. That's kind of the classical definition. It's the Pascal that we think of as a Newton per meter squared. But in the field of vacuum metrology, what we're now trying to do is we're trying to move to a more quantum definition of pressure. Now, you don't have to understand quantum mechanics, or nor is this definition really quantum, and I'll try to explain what we mean by quantum in a few moments, but it underpins new standards that are based on quantum mechanics. And this new idea is to not think of a Pascal as a Newton per meter squared, but to think of a Pascal as a joule per meter cubed. And joule is the SI unit of energy, and a meter cubed is obviously a volume. And so how do I think about this? If I have a bunch of gas molecules inside a volume, if I know the number of molecules inside the volume, that is to say the gas density, and these molecules are all flitting around and they have some kinetic energy associated with them, that kinetic energy is set by the temperature. So if I know the temperature of the gas, and I know the number of gas molecules or atoms inside this volume, I know the pressure. And so in this sense, the Pascal now becomes traceable not to the kilogram, the meter, and the second, but it becomes traceable to the Kelvin and the second. Now you might say, well, why the second? Well, that's where quantum mechanics comes in. Now I'm going to try to tell you about 2. My abstract said I was only going to tell you about 1, but I'm going to try to tell you about 2 of these measurement devices that we are working on at NIST. And the first operates kind of at that atmospheric pressure and below. And its principle is based on index of refraction. So you may remember from optics class that light moves at the speed of light. Right? We always think of light moves at the speed of light, which is defined by c, 3 times 10 to the 8 meters per second. But that's only true in a perfect vacuum. It's not true in air. It's not even true in imperfect vacuums. And we can quantify, because as you put light through a medium, it slows down, right? And so the true velocity of light is equal to the speed of light in a vacuum divided by a number that we call the index of refraction. The index of refraction is a number which is greater than 1. And it need not be much greater than 1. For example, if you take a nitrogen gas and you have it at 1 kilopascal, which is kind of low vacuum, n minus 1, the difference of n from 1 is only about 3 times 10 to the minus 4. That's 300 parts per million. So it's not a very big shift in the speed of light, but it is indeed there. And if you slow down the light, by inserting a medium, what's going to happen is its wavelength is going to increase. And that's the effect that we're going to try to use to make a vacuum gauge. So the way we're going to actually turn this into a realizable measurement is we're going to use a special tool called the Fabry-Perot cavity. So a Fabry-Perot cavity is when you take two mirrors and you space them by some distance L. And now I take my laser light, my monochromatic light that has a well-defined frequency, and I shine it into this cavity. We call it a cavity because the light will nominally bounce back and forth between these two mirrors, provided that we meet a certain resonance condition. That is to say, that the number of wavelengths of light that I insert into this cavity is a half-integer multiple of the length. And so if I denote the length by L and the wavelength by lambda, my resonance condition is L is equal to lambda by 2, lambda, 3 lambda by 2, et cetera, et cetera. I can turn this around in units of frequency. You may have heard the old joke, what's new? It's C over lambda. Nu is the typical unit that the typical Greek symbol that we use for frequency. In this particular instance, because I'm thinking about gas that would be traveling through a medium, I think of it as the velocity of light divided by the wavelength. And I can insert this resonance condition and I come up with an equation for what the velocity of light should be. What the frequency of the light should be in order to resonate with inside this cavity. So what does this look like in practice? In practice, I build one of these cavities and then I go grab my laser off the shelf, which I can tune the frequency of. And so what I have here, what I'm trying to depict here, is if I plot up the transmission through the cavity, and the cavity will only transmit out the far side if there's light bouncing in between these two mirrors. If I plot up the transmission of the cavity as a function of the frequency of my laser that I'm using to try to inject light into the cavity, I'll get two peaks. I get many, many peaks over and over again, but I'm just showing two of them here. And these are peaks where I fit in another half integer of wavelength into the cavity. Now, these peaks, I've shown three different peaks of different widths. The reason they can have different widths is because of the reflectivity of the mirrors. As I increase the reflectivity of the mirrors, I increase the quality factor of this optical resonator, and I make these peaks narrower and narrower. And so I can get more and more frequency resolution by using better and better, more and more reflective mirrors. Now, I'm out to measure pressure, so how am I going to do that? Well, actually now I take two of these cavities and I smash them against a single piece of glass so that they have exactly the same length. And I'm going to leave one of them empty, and I'm going to start putting gas in the other one. So if I have them both empty, they should nominally be the same cavity, they should nominally give me the same spectrum. But if I now insert gas, because the index of refraction is changing in that cavity, it's going to change the resonance condition, and it's going to shift the peak. And as I insert more and more gas, it's going to shift the peak more and more. And so now what I can do is that I can measure the frequency difference between this peak and this peak, and I can have a proxy for the amount of gas that I've added. Now you may be saying, well, that's great. That all sounds fantastic in practice. But how do you know how much gas there is for a given frequency shift? It's an excellent question. Luckily, we have come a long way in our ability to do atomic physics calculations. And so we can calculate for certain very simple gases what the relationship is between density and index of refraction, and therefore what the frequency shift here is and pressure. This relationship is defined by what we call the molar refractivity constant, and it can be calculated to about part per million level for gases like helium. And theorists are now working on doing more complicated noble gases like neon and argon. And when I say more complicated, I mean they're more complicated in the sense that they have more electrons. So we have this for helium. So if I just fill this cavity with helium gas, I can plug in my theorist numbers, and I can get out what the refractivity is. And because this was calculated with quantum mechanics, you can now see why I was calling this a quantum-based standard. We're using quantum mechanics to get at the heart of how the response of this device works. So at NIST, I haven't been a part of the team that's really developed this concept into practicable devices. They're in my group at NIST, and they continue to work very hard at making these practical devices. They've come up with several different kinds of iterations of these devices. The first one that they made is circa 2012 is shown here. And you can see the two optical cavities here. You can see the bore for the lower optical cavity and the mirror here at the front. And on the top, you can see the front mirror, and you see that there's a slit here. That's the slit that allows gas to enter in the upper cavity. And this is connected to plumbing that keeps this bottom cavity constantly evacuated. We've since moved on to shorter cavities with better, higher mirror finesse. This allows us to go down to lower pressure. And we're also now experimenting with invar cavities, which allow us to go to pressures above atmospheric pressure. And these honestly cover a lot of the vacuum gauge landscape. They can replace a lot of different gauges, including this one here. This has been kind of the standard of vacuum metrology since it was invented in the 1600s. It's a mercury manometer. And in fact, we still have mercury manometers at NIST, which we use to define pressure in the vacuum range. But we're working on replacing these with these new, what we call fixed length optical cavities for realizing pressure. Okay, so I've told you about the flock that we've developed at NIST, and it covers a pretty wide range of pressures using these three different kinds of realizations of it. But that kind of covers a lot of vacuum metrology and an important range for old-fashioned semiconductor manufacturing, food processing, aerospace, and a whole host of other applications. But what about those newfangled applications that are coming down the pike, the ones with new semiconductors like EUV semiconductor manufacturing and those new quantum platforms? How do we measure vacuums in that regime? Well, this enters into the project that I've been a part of for now the better part of a decade, which is the cold atom vacuum standard. So let me try to give you a picture of how the cold atom vacuum standard works before I show you pretty pictures of the gauge itself. So what we try to do in the lab is we take a gas of atoms, we laser cool it to near absolute zero, and when I say near absolute zero, I mean about 100 microkelvin above absolute zero. That's 100 millionths of a degree above absolute zero. And then we trap it in a conservative magnetic trap. That is a trap which is just deep enough to hold on to these barely moving atoms. So we've got this cloud of laser-cooled atoms. It's sitting in a localized piece of space, and it's in the vacuum that I want to measure. Now, this vacuum that I want to measure is not perfectly pure. There are still some gas molecules fluttering around in it. And so these gas molecules, if they come by and they strike one of these cold atoms, because there's a huge energy mismatch, these molecules that are left over in the vacuum are not laser cooled. They're probably at room temperature, whatever the temperature of the vacuum chamber is. They're moving really fast, hundreds of meters a second. My cold atoms are moving maybe centimeters per second. When these things come and they strike one of these cold atoms, with near unity probability, they're just going to eject it straight from the trap. And so that's what we're trying to depict here. Our background gas are these red molecules, and they're bouncing into these cold blue balls, which are our cold lithium atoms, and ejecting them from the trap. Now, if you think about the signal that's going to come out of this device, it's an exponential. So if I was to track the number of cold atoms that I have in my trap as a function of time, it would decay exponentially. And the key is that this exponential decay constant is the product of two things. The gas density, that is to say the density of these red molecules that are bouncing into it, and what we call the loss rate coefficient, this L. Now, the loss rate coefficient, if you're thinking about collisions in physics, you might be thinking about things like cross-sections. And indeed, this loss rate coefficient is related to the cross-section of collision between one of these hot molecules and one of these cold atoms. And well, maybe not me, but one of my theorist colleagues who is much smarter than me and has access to really good computers can calculate what is that cross-section from quantum mechanics and first principles. And so we have an excellent colleague by the name of Ida Tsinga, and he can actually run these calculations for us and tell us what this loss rate coefficient is. And so now all I have to do is I have to measure the exponential loss rate of the atoms from the trap, plug in my theorist colleague's number for L, and bingo bammo, I have a measurement of the background gas density or pressure. Now, because all I'm measuring is a loss rate, the only thing that I'm really measuring is time. I'm measuring a time that it takes for 1 over E of the atoms to disappear. So I'm measuring seconds. In addition, if I do honestly want to change it into pressure, I have to multiply by the temperature, so I have to measure the Kelvin as well. And so now my measurement of pressure is traceable just to the second and to the Kelvin. Because it's traceable to base units and not a unit of like kind, this is what we call at NIST a primary standard. It is a way of realizing a measurement of pressure that doesn't rely on any other measurement of pressure. It's completely primary. Okay, so wait. I may hear some of you cry. What is laser cooling you speak of? How do you get a cold cloud of atoms? How do you get a cloud of atoms interacting with laser beams to get down to 100 microkelvin? Well, luckily I stand on the shoulder of giants at NIST, and so laser cooling has been developed since the 1970s, was the first theoretical proposal by Dave Wineland, and it was subsequently developed experimentally and even further theoretically by Bill Phillips, Steve Chu, and Claude Cohen-Tanuji. And the basic ideas of laser cooling that you need to keep in your head to understand it are 3 things. Atoms are quantum systems. The Doppler effect for light is exactly like the Doppler effect for sound. And the last thing they have to bear in mind in order to understand laser cooling is that light carries momentum. And now let's try to combine those 3 things and see if we can figure out how laser cooling works. So the first thing I said was atoms are quantum systems. What do I mean by that? I mean that the electron, as it travels about the nucleus, can only exist in certain quantized energy levels. And I'm an atomic physicist, so I like to draw diagrams like this, where I depict the energy levels in an atom as horizontal bars. I label them G and E. And if I were to take a laser that was tuned to the correct frequency, that is to say, the frequency, when I multiply that frequency by Planck's constant, is equal to the energy separation between these 2 states, I will drive a resonance in this atom, and I'll drive that electron up to a higher orbital, back down to the lower orbital over and over and over and over again. But what these guys realized is you don't necessarily want to do that. If you just take the laser and you, what we call red to tune it a little bit, you tune it such that its frequency is just slightly below the resonant frequency where the atom will absorb and emit all these photons, you'll get an interesting effect. And that interesting effect comes from the Doppler effect. So now imagine I'm an atom and I'm not moving and I shine a laser on me, or let's say Larry was standing over there and he shines a laser on me that is just shy of my atomic resonance. What will happen? Basically absolutely nothing. That laser will fly straight through me. It will not interact with me because I only have quantized energy levels, and so that laser is tuned to not the correct set of levels. Now, if I'm walking away from that laser, so I'm going this way, now, because of the Doppler effect, it's going to be even further detuned. So if you think about an ambulance that's going past you, as it goes past you, its pitch decreases, its frequency decreases. And so as its frequency decreases, it's getting even further off of resonance, and so you're definitely not going to absorb it. But now if I turn and I walk right into that laser, now it's like the ambulance on the street is coming toward me and its pitch is increasing. So its pitch increases, and now, if I'm moving at the right velocity, it's on resonance. And so now I absorb a photon from that laser beam. And here's where the third thing comes in. Once I absorb a photon from that laser beam, I get a little bit of a momentum kick. Now, light doesn't carry a lot of momentum, but it carries enough. It's kind of like throwing ping pong balls at a train. But if you throw enough ping pong balls at a train, you will indeed get it to stop. So now I go in, I absorb that photon. I get a little bit of momentum kick. It slows me down. And now I'm in the excited state. I'm not going to be up there for very long. By Heisenberg's uncertainty principle, I'm going to have to decay back to the ground state. And when I decay back down to the ground state, I'm going to emit a photon. But the key is I'm going to emit that photon in some random direction, right? And if I emit it in a random direction, and this process is repeated over and over again, that's going to average to 0. So every single time I go through this process, I'm going to slow down a little bit. And so this is laser slowing. How do I get laser cooling? Well, you actually take, I should say, by the way, this idea was so revolutionary that it won all 4 of these guys, it won 3 out of the 4 of these guys a Nobel Prize. Dave Wineland proposed this idea in 1975. He was not amongst the winners in 1997 of laser cooling, but he would win the Nobel Prize for other reasons in 2012. So how do you get laser cooling instead of laser slowing? Well, you actually take 6 laser beams and you shine them along all 3 spatial dimensions. So now if I'm an atom, I walk in any direction, I'm going to get slowed down. Now, I'm not going to go into the details of this right now, but if you were to add a magnetic field gradient to this setup, you can also get spatial confinement, provided that you tune the polarization of your laser beams in just the right way. And that creates what we call a magneto-optical trap. It's the workhorse of atomic physics since the 1980s. Basically, all cold atom apparatuses start with magneto-optical traps because they are so efficient at taking hot atoms and making them so close to absolute 0, and they do it within a few hundred microseconds. It's really impressive technology. All right, so I'm going to make a cold atom vacuum standard. I'm going to use laser-cooled atoms. Here's a periodic table. Which atom do I pick? Well, good news is, at least for me, not all of these atoms have been laser-cooled. But I'm kind of curious, what fraction do you think of this periodic table has been laser-cooled? Anybody think more than 50%? No? How about less than 10%? A few less than 10%. How about less than 30%? Okay, so here are the atoms that have been laser-cooled. I think that's about maybe 10% or so. It looks like that. But it's a fair number, all from around the periodic table. We've got the noble gases, the alkalis, the alkaline earths, transition metals, even aluminum, gallium, and indium. I'll point to this one, molybdenum. And the reason I'm pointing to molybdenum is because that was just laser-cooled last year in my group. So we were able to add to the periodic table of laser-cooled elements. I was pretty pleased about that. So what does this look like in practice? This is what we call the laboratory cold atom vacuum standard. It is kind of a quintessential laser cooling apparatus in atomic physics. As you can see, it's really rather complicated. It's basically, first, a giant vacuum chamber. So this vacuum chamber is divided into 2 parts. This part back here is what we call the source part, and this part up here is what we call the measurement part. And in the source part, we first make alkali atoms that are going to be laser-cooled. I didn't mention this in this last slide, but the laser we love to pick is lithium because it's light. And so we make lithium atoms by basically taking a chunk of lithium metal and heating it up by running current through a stainless steel cup that holds onto the lithium atoms. Heats it up, sublimates gas into the vacuum chamber. Then we hit it with 4 laser beams, which are depicted by these red arrows. 1, 2, 3, 4. That makes what's called a 2D magneto-optical trap. When you combine it with the magnetic fields generated by these magnets, there's a little bit of forward momentum that carries the atoms out of the 2D magneto-optical trap into a 3D magneto-optical trap. That's made by 6 beams, which are coming in over here, 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 and here. They're cooled by these laser beams, but not fully trapped. We need these magnetic coils in order to do that as well. So we over-engineered these beautiful electromagnets here that can dissipate many kilowatts of electrical power without raising their temperature more than a couple degrees, requiring hundreds of amps of current. As you can see, this is a very complicated apparatus, but we built it because we wanted to understand all of the potential pitfalls of trying to do a vacuum measurement with cold atoms. This gives us basically control over every conceivable aspect of the measurement. But you're never, ever going to use this in a practical way to measure vacuum. Especially, I should point out, by the way, this is also a meter long. This is a big thing. But you're never going to use, and just in case you've never seen a picture of laser-cooled atoms before, I threw this in. So this is actually the very first magneto-optical trap that we made in the laboratory scale cavs, circa about 2016. So what you're seeing here in the center, this is a glass vacuum cell. So inside here is a very pure vacuum with the lithium atoms that we're going to laser cool. And you can see the diffuse reflection of 6 laser beams, 1, 2, 3, and 4 coming in from the sides, and 1 and 2 coming in from the top and bottom. And then at the intersection of those 6 beams, this little dot here is about 1 million lithium atoms cooled to, in this apparatus, about 300 or so microkelvin. And this picture, by the way, I just took with my cell phone. Lithium is a beautiful atom, in my opinion. It fluoresces at 671 nanometers. It's a beautiful, bright red cherry color. And so cell phones are excellent for picking it up and taking pictures of it. Okay, so as I was trying to say, nobody's going to build, though, this extremely complicated apparatus in order to do a vacuum measurement, especially when you can grab one of these. This is the quintessential tool for measuring vacuum today in the ultra-high vacuum and the extreme high vacuum range. It's what's called an ionization gauge. And if it looks like it's straight out of the vacuum tube era, if that's what you're thinking, you're absolutely correct. It is straight out of the vacuum tube era. It, in fact, operates very much like a traditional vacuum tube. But it's still the best way that we can measure these vacuums. And in fact, these EUV lithography machines, they have them on them. It's not important how they work. What I'm going to tell you tonight is that they're basically unreliable. I was taught as a graduate student to never trust them to within a factor of 10. You can get these calibrated at NIST. It'll cost you about $13,000 or $14,000, I think, to run a calibration of a single ion gauge. And then you have to be very careful with it, because if you upset the geometry of any of these electrodes that are sitting inside the gauge, your calibration's useless. It'll change. And so this is not a very high accuracy device. So we'd really like to get rid of these at the point of use and replace them with these cold atom gauges. But to do that, we need to take this giant laboratory apparatus and need to strip it of all of the unnecessary components and shrink the other components down so you get something that's more akin to this. And so for the vast majority of the project, we spent a lot of effort building up this, what we call the portable cold atom vacuum standard, or the PCAVs. And this takes all of the apparatus, that 1 meter long apparatus, and simplifies it to a package which is, I'm going to admit, not quite the size of an ion gauge. An ion gauge is about yay big, but one of these is about this big. It has all of the same features of the laboratory cavs that are essential. So at the bottom here, there is a source region. That's the thing that has the dispenser, which makes the lithium atoms that we're going to laser cool. That dispenser emits these lithium atoms. They travel up what's called a differential pumping tube into this region here, which is what we call the measurement region. And so we have these 2 separated regions, but it's, again, much smaller device. And instead of having 6 laser beams come in from all 3 spatial dimensions, which is the thing that makes the laboratory cavs so complicated, we instead replace that with a single beam that comes in from the top and a very special nanofabricated diffraction grating that sits here on this platform. And you can see a picture of this nanofabricated diffraction grating, which was manufactured in our clean room at NIST Gaithersburg by my colleague Nikolai Klimov. And what this chip is essentially a diffraction grating, or 3 diffraction gratings arranged in a triangular pattern. So that when you shine a laser beam on the top, from the top, it strikes this grating, it makes 3 additional laser beams that come up from the chip, kind of in like a tetrahedral geometry. And if you think about what I said earlier about laser cooling, what you really need is you need enough laser beams that they all have a projection of momentum along 3 spatial axes. You don't actually have to have 6 laser beams. In n dimensions, you just need n plus 1. And so here, this chip combined with the laser beam that comes in with the top makes the minimum number of beams required to laser cool atoms. And so we can form a magneto-optical trap right here about a few millimeters above this grating chip. And this device is so ridiculously simple, it operates with 3 switches. And it operates in time scales that humans could actually flip these switches. So we have 2 kinds of light that we shine onto the atoms to do the laser cooling. For the purposes of this talk, I'm just going to refer to them as cooling light and repump light, but they drive 2 different transitions in the lithium atom that are important in order to make the laser cooling process work. And then there's a 3rd switch, which is a little piece of metal. We call it the atomic shutter. What it is it just flips up. It's a little piece of metal attached to an actuator, which flips up and blocks the flow of lithium atoms from the dispenser into the measurement region. And so to start the entire measurement process, we need to first make laser-cooled atoms. So we flip all 3 of these things on, and that forms a magneto-optical trap. And that magneto-optical trap takes literally a few seconds to load. You can actually watch it load and get brighter and brighter and brighter. And for a magneto-optical trap, it's an object that's fluorescing, and the amount of fluorescence that comes from the magneto-optical trap is a very good proxy for the number of atoms that are in it. And so as you see this thing get brighter and brighter and brighter, you can see that you're collecting more and more atoms. And at some point, we need to turn this loading process off. And so after, say, about 3 seconds of loading, we snap a picture with a camera to detect the amount of fluorescence that we have in this MOT at the end of the loading process. And then we close the atomic shutter to stop the flow of more lithium atoms getting into the MOT. And we turn off what's called the repump light. And then what that does is it uses the cooling light to dump the atoms into a quantum state, which is trapped just by the residual permanent magnets that are installed on the side of the PCAVs. We then hold those atoms in this magnetic trap for some period of time, anywhere between 1 second and 180 seconds for the work that I'm about to show you. But we've since done more work, and can get this now to about 15 minutes that we can hold on to the atoms for. And my goal when we started the project was to be able to hold on to atoms for about an hour. So we're getting close. At the end of that time, where these atoms are just being trapped by the magnetic fields of the permanent magnets around the PCAV's device, we then turn the laser light back on. Just the laser light, not the atomic shutter. And what that does is it recollects all of the atoms from the magnetic trap and captures them back again in one of these magneto-optical traps. And the magneto-optical trap that we end up with at the end of this sequence is less bright. It's dimmer because we've lost a bunch of atoms from collisions with the background gas. So we can plot this up on a log linear plot, and after this entire measurement process, we get 1 point. Okay. So I've explained all that, and I got 1 point on this graph. Now, when we built the PCAVs, remember what I told you. This is going to be a standard. Now, a standard is only useful in that if I build a standard and I build another standard, these 2 standards ought to agree, right? So a good first test as to whether or not you have a standard is to build 2 of them and compare them against each other. And so that's exactly what we did when we first realized this PCAVs was we built 2 of them. And it turns out vacuum equipment's inexpensive compared to lasers. So we had 1 laser and we just switched using a fiber switch which laser this thing was interrogating. So then we would repeat this process. We would start this process with what we would call PCAVs number 1, which is just a number, just an identity number. We would then switch to PCAVs number 2 to repeat the measurement. And now we would switch back to pCavs number 1, but do a different hold time. That gives us another point on this log linear plot. And then do pCavs number 2 and a different hold time, and slowly but surely build up data on this log linear plot. Now, just in case you're unfamiliar, when you plot up an exponential decay on a log linear scale, it looks like a straight line. And the slope of that line determines the loss rate in that exponential function. So what we were expecting to see was, as we switch between these two pCavs devices, we were expecting to see, well, maybe they're offset from each other, but they should have the same slope. And indeed, when we tested these two devices, that is indeed exactly what we saw. We saw two devices, whoops, wrong button. We saw two devices that had different offsets because they're different devices, but they had the same slope. So yes, these things are acting as standards, two completely independent devices. They have some differences about them. They're mostly similar, but they're two independent devices, and without any calibration, without any real effort from us, they gave us the same answer. That was very encouraging. We've demonstrated the first thing that you would expect to see if you have a standard. Now, you might say, okay, well, what's the pressure? Well, I can take the fitted loss rate here, plug it into, take my theory colleagues' numbers for the loss rate coefficient, plug them in, divide them, and I can get a number. And for this particular measurement, these two devices were looking at the same vacuum. They were attached to the same vacuum chamber. They were literally looking at each other. They had a direct line of sight toward each other, so they should be at the same vacuum pressure. And this vacuum pressure happened to be very solidly in what we would call the ultra-high vacuum regime. Now, what I just told you was a complete lie. Because anytime you do science, it never really works the first time, right? You always have to do something. There's always something that goes wrong. And so this is what we actually saw when we first turned the two pCavs on. They're supposed to see the same thing, and we did not see that. And I saw this graph for the first time. We had an excellent undergraduate by the name of Lucas Ehinger working on this. And Lucas showed this graph to me, and my heart sank. I was like, we've been thinking that these things should be standards, and they're not standards. They're not. Look at this. This is terrible. And so your mind, when you get into one of these situations, immediately goes to thinking, it must be the new thing. The new thing is the thing that's the problem. And so we start trying to figure out why the two devices are giving us different answers. They're nearly identical. Let's start switching components. Let's test this. Let's test that. And for about 2 months, nothing we could do could change this essential graph. pCavs number 1 was decaying with a loss rate that was greater than pCavs number 2, despite the fact that they should be looking at the same vacuum. And finally, it just dawned on me. I was like, well, maybe we should listen to our standards. They're supposed to be able to measure the pressure in a calibration-free way. And what they're telling us is that they're seeing two different pressures. Maybe that's what's actually going on. And I am so sad that it took me 2 months to figure that out. Because the moment I had that thought, we whipped out our leak detector, and sure enough, there was a leak in the pCavs number 1 device that was causing it to be at a slightly higher pressure than pCavs number 2. So the lesson here is, if you have a standard, you should trust your standard. Now, one of the beauties of an ionization gauge is that, and I showed you a picture of what we would call the sensor head. It's a very simple device which is controlled by a piece of electronics which is no bigger than that. Now, you might think, well, a laser-cooled apparatus, you have the apparatus part, you have the sensor head, but what does all the support electronics and optics and all that stuff look like? And at the time that we did that experiment, it was scattered all over the lab. We really had no good sense of how you could, of how we could simplify all of the infrastructure that you need in order to run this apparatus. And a couple summers ago, I had a summer student come through the lab, and he actually, Jeremy Robin, and he actually built this equipment rack, which racked up all of the necessary electronics and lasers that we need to run this portable cold atom vacuum standard. Now, an equipment rack is much larger than a piece of electronics, which is bigger than this, but I'm a physicist, I'm not an engineer, so I look at this and I see progress. I feel like if an engineer were to take it over from here, they'd be able to shrink this thing down into something that's far more manageable. So that's where we are with the PCAPs. We now have a demonstrated standard that's able to measure pressure in the ultra-high vacuum regime. And so we're able to fill in this gap in the ultra-high vacuum and the extreme high vacuum. So I always say that none of this work happens in a vacuum. There's been a lot of people that have worked on this cold atom vacuum standard. I am just one member of the team. The main 4 people that have been behind it for the last decade are myself, Jim Fedchak, and Julia Scherschlicht, and Dan Barker. Dan Barker was my first postdoc, and he's still at NIST working in my group. We've had excellent theory collaborators, Jacek Klaus and Ida Tsinga. We've just hired a new postdoc, Isaac. We've had several alumni, and I also want to thank my collaborators as well. And I'll leave you with this, which perhaps I should have shown a picture of earlier. So this is a picture that one of our public affairs officers took with his nice DSLR camera, looking in through one of the viewports at our portable cold atom vacuum standard. And so that chip that I showed you that had the triangular grating is down here on this platform. You can see the triangular hole that was in the center of the chip right there. And there's a laser beam coming down from the top, and right there is a cloud of about 100,000 laser-cooled lithium atoms. So with that, I will thank you for your attention.
So we have time for questions. I think you probably all know the procedure, but if you don't, we have microphone runners with microphones that have wind screens, which are red and blue, and I will keep your hand up. Don't be shy. You keep your hand up. Eventually, somebody will bring you a microphone. And when you get the microphone, I will be calling on people by the color of the windscreen. When I call your color, you stand up, tell us your name, tell us if you're a member, and ask a question. We save the speeches for later, except me. I have special privileges. We need another microphone runner. No takers, huh? We'll start with the red microphone here.
The name is Al Ehrlich. I am a member. And it's been a while, but I used to work side by side with people who were doing MBE, and their instruments. My last question is going to be, what are the units? They used to work with instruments which were, I think, routinely they thought were 10 to the minus 10th to 12th or something like that. Are these the same units you're talking about?
Yeah, so...
And how did they achieve that so simply?
MBE machines, molecular beam epitaxy machines, these deposit layers of atoms in crystals, one atom at a time or one layer at a time. And they routinely operate at pressures that in the units that I'm talking about are about 10 to the minus 10 Pascal to 10 to the minus 8 Pascal. Now the numbers you're quoting, there are a whole bunch of different units to quantify pressure. One of the more common ones is torr. And the difference between torr and Pascal is about a factor of 100. So 10 to the minus 10 Pascal is about 10 to the minus 12 torr. 10 to the minus 8 Pascal is about 10 to the minus 10 torr. So that's probably where they were operating.
Thank you.
Yeah.
Got the blue microphone, please.
I'm Bob Hershey. I'm a member. What kind of process would you be measuring where you're looking at the vacuum, and how much does what we just saw improve it?
So there's lots of different scientific instruments and industrial processes that look at vacuums. The vacuum ranges that the techniques that you would use depend on the vacuum range of interest. So for the places where this gauge operates, which is about 10 to the minus 5 Pascal and below, the only other alternative is an ionization gauge. In an ionization gauge, you can say that the uncertainties, if you know that the gas that's left over in your vacuum chamber or the process gas that you're using is nitrogen, you can sometimes get the uncertainties there to be about 3% is a typical number. With this gauge, with nitrogen, we could do about 1%. So it's about a factor of 3 improvement. Now, I'll take this opportunity to talk down on ion gauges a little bit more. So ion gauges are extraordinarionally sensitive to gas species because what they're doing is they're ionizing the gas that they're trying to measure. So and ionization potentials differ very greatly from gas to gas. So if I have a vacuum chamber that has nitrogen in it, and then I switch from nitrogen to, say, helium, the ionization potential of a nitrogen molecule and a helium atom are extraordinarily different. And so the response of the gauge is going to be extraordinarily different. These cold atoms these are neutral atoms, and they're colliding with background gas molecules through a force which is the van der Waals potential. Now, the van der Waals potential is much less species dependent. And so you can commonly see, as you switch process gases with an ionization gauge, factors of 5 difference in sensitivity. With this gauge, maybe 20%. So it's much less gas species specific. And so for vacuum chambers where you don't know the gas concentration, what the gas is actually made of, this is going to be a better choice by far.
Red microphone?
David Rosen, member. 2 questions. At this low pressure, are there any diatomic molecules or are they all atomic gases?
There's a mixture of both. So at these pressures, in a stainless steel vacuum chamber, you're likely only to find hydrogen molecules and water molecules. And the reason for that is as follows. So if I take a stainless steel vessel, which I'm going to evacuate all the air out of, I hook up my giant pump. My giant pump starts to pump out the air. And the nitrogen and the oxygen are, relatively speaking, not very reactive. And so they get pulled away pretty quickly. Water, on the other hand, is very sticky. It likes to stick to metallic surfaces and form oxides. And so these monolayers of water take a lot longer to kind of peel off. And so you'll often find after you've removed all of the air, there's a lot of water remaining. And then if you used stainless steel to build your vacuum chamber, there's another effect which happens, which is that in the process of making stainless steel, you actually trap atomic hydrogen in the stainless in the form of ions. And these ions start to diffuse through the stainless steel, and they eventually get close to the surface, and they can't quite free themselves into the vacuum until they meet up with another hydrogen ion, form a molecule, and then they can be released in the vacuum. And that process of hydrogen outgassing is indeed the limiting factor in the vast majority of vacuum chambers.
Another one. You said how you cool laser cooling. You described that well,
yes.
But how do you measure the temperature? What's the difference?
So measuring the temperature of the cold atom cloud is impossible. Well, maybe not impossible, but I have yet to figure out a good way to do it with this portable CABS device. The good news is temperature of the atomic gas doesn't matter. It's only the temperature of the background gas molecules that actually matter for the measurement. Now, traditionally, if I have a gas of cold atoms that I've laser cooled, the way I would measure the temperature is to just let it go. Because if I let it go, the atoms will move with whatever velocity that they randomly had. And then I can watch this gas expand. And the rate of expansion tells me what the average velocity of the atoms was in the gas. And the average velocity tells me what the temperature is. And so this, what we call time of flight technique, is the go-to standard for how to measure the temperatures of these really, really cold gases.
We'll take a couple of questions from the web, then we'll go to the blue microphone, then we'll go to the red microphone. Web, blue microphone, then red microphone.
All right, first question from the web is from streaming from Florida, Jim Tallons, who is a member. If it were possible to reach an absolute zero, what would you see and what would happen, and why is that apparently impossible?
So I assume we mean an absolute zero in temperature.
Yes, sir, Kelvin.
So absolute zero is not attainable because of what's called the third law of thermodynamics. So the third law of thermodynamics says that you cannot reach absolute zero in a finite number of thermodynamic steps. There's no thermodynamic engine that you can build with a finite number of steps that'll get you down to absolute zero. So as you get closer and closer to absolute zero, what you see is kind of the effect that I just described. So to be honest, I was advertising that these atoms get down to a few hundred microkelvin. That's actually rather hot compared to what you can, with the state of the art in the field. The coldest temperature that I can recall off the top of my head is closer to 100 picokelvin. And what happens at 100 picokelvin is basically the same thing that we see at 100 Kelvin. You still have a gas of atoms, they're just moving even more slowly on average than they were moving at 300 Kelvin. Now you might wonder, okay, why don't they condense? Why don't they do something else? Why don't they form a different state of matter? They will if you have the correct density. And so for these are very dilute gases. They'll always be gases. They won't phase transition to some other phase, which is, I think, what the question's kind of alluding to. So depending on the density with these kind of cold atomic clouds, you could get a quantum degenerate gas, or in the case of that 100 picokelvin, the density was still low enough that it was still very much just a dilute gas.
Second question?
Second question from the web, from Ranju Rajimanath, a member streaming from Germantown, Maryland. Would you be able to name a few applications of measuring vacuum in the area of medical research or therapeutic development?
So at these vacuum levels, I'm going to struggle to name an application relevant to medicine. At lower vacuum levels, kind of the low vacuum and medium vacuum, is where you'll see potential applications, particularly in pharmaceuticals for safety and things of that nature. But at these really, really, really low pressures, at least I can't think of any application immediately relevant for medicine.
Thank you.
Blue microphone.
Yes, James Cole, a member. I have two questions. One is a simple technical question. In your Fabry-Perot interferometer, I noticed that one of the lenses was one of the mirrors, I should say, was concave. Why the concave mirror?
That is an excellent question. So if you take two parallel mirrors, two flat mirrors, and you try to make a cavity, you need to have the light bounce back and forth over and over and over and over again. So if you take two perfectly parallel mirrors, in order to make that happen, you would have to ensure their parallelism to an ungodly degree. And so it's just not practical to build a Fabry-Perot cavity out of two flat mirrors. So what we do is a little trick. We take this mirror and we curve it a little bit such that it has a focal point right at where the flat mirror is. And that way, if they're not perfectly parallel, you'll still get repetitive over and over reflections.
Okay, thank you. Now, the second question, you mentioned you're going down to 10 to the minus 10 torr. Now,
Yes.
in physical terms, how many molecules or atoms per square meter might be striking a surface per second?
Yeah, so the number I like to keep in my mind is the density of a gas, of an ideal gas, at standard temperature, at 10 to the minus 12 torr, has only 10,000 atoms or molecules per cubic centimeter. So I just clasp my hand like this. I've captured about a cubic centimeter. If this was 10 to the minus 12 torr, which is 15 orders of magnitude lower than atmospheric pressure, I would only have 10 to the 4 atoms in my hands.
So you might even see statistical fluctuations.
Absolutely, you would probably
All
see
right, and then that
statistical
follows up.
fluctuations. Yeah.
Then there would be some radiation pressure.
You have
How
to
would the
talk into the
radiation-
microphone.
Yeah, sorry. There might be some radiation pressure. And how would this radiation pressure compare with the pressure due to the impacts on your hypothetical pressure gauge? I know it's not a real pressure gauge, but how would it compare? Rough order of magnitude.
Okay. So let me attempt to reinterpret your question just slightly. So imagine I had perfect vacuum, and I made one of these cold atom clouds. It still exists in a chamber at finite temperature, or non-zero temperature, excuse me. At non-zero temperature, the walls of this chamber will be emitting photons, and these photons will be in thermal equilibrium with the walls of the chamber. We call this blackbody radiation. It was Planck's famous discovery in 1901 that he figured out the law that describes the spectral characteristics of blackbody radiation. Thankfully, at room temperature, there are basically zero real photons that can interact with the atoms due to blackbody radiation. Because blackbody radiation at room temperature peaks at around 10 microns, and these atoms only really interact when they're in their ground state with light that's at a minimum of 671 nanometers. So you'd have to go to even shorter wavelengths to see even more atomic resonances than 671. And the fact of the matter is there's just no blackbody radiation down in that range.
Okay, so the physical pressure is much larger than any radiation pressure.
Yeah, the radiation pressure that you're speaking of that would be due to blackbody radiation is completely negligible.
Okay, thank you very much.
Red microphone. Name, membership.
Ciprian Ivanov, member. Was the discovery of how to isolate very low energy molecules the basis for the change in pressure definition?
No, not really. So really the basis for the change in the pressure definition is coming mostly from the redefinition of the SI. So in 2019, the redefinition of the SI, we moved from artifact-based definitions of the units, like, for example, a hunk of iridium metal, or not iridium, platinum metal, excuse me, sitting in a safe in the BIPM at Paris to define the kilogram. We moved away from that toward defining all of the units in terms of fundamental constants. And today, the fundamental constants define the SI. We actually say that the SI is a system of units that realizes the following values for these 7 fundamental constants. And it was this shift from artifacts to physical constants that was the big motivating factor in this shift from thinking about pressure from a Newton per meter squared to an energy per unit volume, because Boltzmann's constant became defined, and we were developing techniques simultaneously that could get at pressure densities using quantum mechanics through the second.
For anyone who's interested in the redefinition, there is a video, PSW video on it, about the time that it was instituted by somebody from NIST. Let's see, we're going to the blue microphone. It's
Okay,
on,
lovely.
just talk into the microphone.
Yes, wonderful. Thank you. Prachi
Name, are
Vakaria,
you a
not a
member?
member. Yeah,
Okay.
I'm with ARPA-I. And my question is, so if you know of nitrogen vacancy magnetometers, they work kind of similarly, where you have a magnetic field that's applied, some, in this case, nitrogen, like diamonds, that goes to quantistate, and then you have this bias magnet, which you read to detect magnetic fluctuations. I'm curious, with this sensor, can that also detect other properties like magnetic fields?
Yeah, so NV centers are excellent tools. They don't just measure magnetic field, by the way, they measure temperature and pressure as well. There's a researcher in my group named Zishan Ahmed who's doing research in this particular topic. Do cold atoms measure similar things? Absolutely they can. So there are researchers at NIST who are trying to use cold atoms to measure magnetic fields. You can also use cold atoms to measure inertial forces. So you can build what are called atom interferometers. These atom interferometers are exquisite tools for measuring things like accelerations. And that includes the gravitational acceleration that's keeping us all bound to this planet. And things like rotations. And of course, I would be remiss if I did not mention that you can use atoms to define time, which is perhaps their most common use, and the use for which NIST is perhaps most famous. So yeah, atoms have a wide variety of different sensor modalities, and this is a platform that could be potentially used to realize them. So in my group, we've been thinking about ways of taking this kind of PCAVS device and turning it into an atom interferometer, for example.
Okay. Very cool. Thank you.
We'll take a red microphone and then a question from the web.
Timothy Thomas, I am a member of the Society. I'm wondering, your decade work on this project has spanned the emergence of these AI tools that have impacted science so immensely. I'm wondering, in your lab, has it impacted you theoretically, practically, programming? Is it the engineers? Who's using it, if anyone?
Yeah. So has it been used by us? Have we? Okay, so we have not directly used AI in our lab. These gauges work on images, right? So we take pictures. We literally take pictures like this one, of cold atoms in order to count the number of atoms there. And so I have always had in the back of my mind something that's like, you know what AI is really good for? Processing tons of images. We should be using AI to process this. And I've had students come through who are very excited about this, but we have yet to have actual progress toward using it for that particular purpose. I mentioned Zishan Ahmed just a moment ago in the context of NV centers. In my group, he's using artificial intelligence tools to actually get out the sensor modalities of nitrogen vacancy centers. So nitrogen vacancy centers are very complex, much more so than atoms. They have unique spectral features. And one of the things that you can attempt to do is deconvolve those spectral features to get at the information you want. And he's using AI tools in order to do that. So, not my lab, but within my group at NIST.
Web?
Next question from the web, from Michael Hocken, member from Silver Spring, Maryland. Slightly surprised that the cold atom standard pressure depends on theoretically calculated parameter. Has any uncertainty of that model calculation been assessed experimentally?
Excellent question. I was hoping somebody would ask that question. So the amount of effort that we put into developing the PCAVs was roughly, I'd say, 30% of the project effort over the last 10 years. The other 70% was directed at answering that very question. So, yeah, you just said that there's a theorist who sat in his office and he calculated a number, and you're just going to use that willy-nilly to tell me what the pressure is? Well, no, I'm not going to do that, because what we need to do is we need to have some sense that that theorist was doing the right thing, right? That his calculation was correct. So we needed to validate that. And so part of the apparatus that we built, here's me standing in front of the laboratory calves. Attached to that, just beyond my head, is a kind of traditional vacuum metrology apparatus. It's a copy of an apparatus that we use to calibrate ionization gauges, but it was custom built to interface with our cold atom vacuum standard. And what this traditional vacuum standard allows us to do is inject a known amount of gas of a known species into a calves to measure. And so now we can use this classical vacuum metrology tool to measure those loss rate coefficients that the CAVS uses. So now I have an independent measurement of the loss rate coefficient, and I have my theorist colleague's number. And we spent probably about 4 or 5 years working on building up this measurement, and then an additional 2 years actually performing the measurement. And lo and behold, my theorist colleague was right, and his numbers were all in agreement with our experimental numbers within their mutual uncertainty. Now, there's another caveat there, which is that my colleague, my theorist colleague, was actually able to, because he's at NIST, he's very concerned about uncertainties, and he actually developed a technique to establish an uncertainty on his theoretical calculations. And so we have our theoretical uncertainty and we have our experimental uncertainty. And now we can evaluate how well these two things agree within their mutual uncertainty. So we tested 5 different species of gas colliding with lithium atoms and 5 different species of gas colliding with rubidium atoms. And we found mutual agreements within 90% confidence for 9 out of the 10 combinations. So our theorist friends were, in fact, really smart and got the right answer.
Thank you.
And the 10th one?
I'm still thinking about the 10th one.
Red microphone, maybe the last question.
Yes,
Oh,
Richard
no,
Talbot,
got one here.
proud member of PSW. Very impressive presentation, thank you. But we're not done yet. I was wondering if you could just summarize what's involved in going down and measuring pressure at the quantum level.
Pressure at the quantum level.
We talked about Kashmir plates briefly.
So, I'm trying to think of the best way to address this question. So, if you were to so there's an entirely different concept of what, I've given you a very classical conception of what a vacuum is. I have some sort of a chamber, it's filled with gas, I try to remove all of the gas particles I possibly can. But there's actually a more quantum mechanical view of what vacuum is, which is even if I have nothing in some region of space, there's still quantum fluctuations within that region of space, like virtual particles that are popping up and disappearing constantly. And these fluctuations actually do indeed cause a pressure. Now, the most common way that people think about this pressure is the so-called Casimir effect. And my thesis advisor at Yale University, Steve Lamoureux, was one of the first scientists to really probe the Casimir effect experimentally. So what the Casimir effect is if I take 2 metallic plates and they're grounded so that they're exactly the same electrical potential, they will still experience an attractive force between them. And the reason is because the quantum vacuum fluctuations on the outside are larger than the quantum fluctuations in between the plates, and so there's kind of like a pressure which pushes them together. That's one way of understanding the Casimir effect. And the way that you measure that is the way my advisor did, with 2 parallel plates, right? This device can also potentially, there are people who are thinking about if you can measure Casimir-like effects with atoms, and people who are doing experiments along those lines. And it usually involves bringing the atoms close to a surface so that they can feel kind of the electromagnetic vacuum in the vicinity of the surface. But I think that is not necessarily a unique view of the effect that we're talking about, because you can also view the Casimir-Polder force as there are fluctuations of the electrons on the surfaces of the electric plates, and these create like van der Waals type forces which draw the plates together. And now I don't have to invoke the quantum vacuum, I'm just invoking thermal fluctuations of the electrons, and actually quantum fluctuations of the electrons on the surfaces of the plates. And so both views, when you go through the mathematics, give you the same answer. And so I've always kind of prescribed to the Lifshitz view of Casimir-Poldar forces, that it's due to fluctuations in the metallic surfaces. But in any event, I've kind of gone on a diversion there because I knew a little bit about it as a result of the fact that my thesis advisor had worked on it. Are we going to be able to measure those kinds of effects with this particular gauge? No, that's not really our objective.
I think the blue microphone's floating around somewhere. Yeah.
Good evening, Pete Waters, not yet a member, but you'll have my application tomorrow.
Yes. All right.
I noticed when you put the periodic table up, talking about which atoms in the periodic table had been laser cooled.
Yes.
All the noble gases on the right side, all the lithium and below on the left side.
Yep.
And I'm wondering if there's some overarching, it sounds like it's valence connected at least a little bit, just by those 2 points. I'm wondering if there's an overarching principle that has an impact on that, and we've just only done spot checks in the middle.
You're absolutely correct. So there is an overarching principle. So basically what you need in order for laser cooling to work is you need a optically accessible transition in the atom that is what we call closed, so that you can repeat the process over and over and over and over again. Because it's not enough to scatter one photon to stop you. Just like the ping pong balls being thrown at a train, you have to have many thousands of photons thrown at you to stop you. And the easiest class of atoms that fit that description are atoms with one valence electron, or atoms with one hole, which you can get in or metastable atoms in noble gases fulfill this criteria. I should put an asterisk next to all the noble gases, because the noble gases all have to be excited to a metastable state in order for the laser cooling process to happen. That metastable state has one valence electron effectively. Likewise, the transition metals and some of the lanthanides, they have like one mostly valence electron. And there's a bunch of core shell stuff that's happening as well, but there's still one electron that you can point to and say that's the kind of acting as a valence electron.
I think you have a question? Can we get the red microphone over here? You go ahead with the red microphone there. We'll get the blue microphone. Put your hand up. Red microphone.
Hi, my name is Navtej.
Hold it up to your...
Sorry. Hi, my name is Navtej. I'm a member. I had a pretty similar question, actually, in terms of, you mentioned there's only 10% of the elements that have been laser cooled.
Roughly, yeah.
Roughly. Like, what are the major limitations towards in achieving laser cooling for more atoms? I think you kind of answered that. But at the same time, my follow-up question was, do you see a path towards laser cooling larger, perhaps molecules, if that's possible, if that's a possibility, and if it is, what sort of applications do you see in regards to that?
So give me an atom and enough lasers, and for each atom, that number of lasers changes because of the different structure of the electrons. But if I had enough lasers, I could probably cool almost any atom. Now, that might be 100 lasers of all different frequencies, so it's impracticable. But like, in principle, if you have enough lasers, you should be able to do it. Molecules are a very interesting field of research right now. So there are groups at several universities and other institutes around the world that are attempting to directly laser cool diatomic molecules and even polyatomic molecules. And the way this works is still very similar to what I just described with respect to atoms. You need to find molecules that effectively have one kind of valence electron, usually, that's kind of tied to one of the nuclei, strongly tied to just one of the nuclei in the molecule. And so this kind of restricts the classes of molecules that you can potentially laser cool. But if you take almost any alkaline earth atom and you mix it with, say, fluorine, that will make one of these potential laser coolable atoms. So strontium fluoride, calcium fluoride, magnesium fluoride. Calcium fluoride and strontium fluoride have indeed been laser cooled. You can take the fluorine atom off and you can replace it with a more complicated, like a OH, and even more complicated than that, and cool a polyatomic molecule. And in our group at NIST, we have another project which is directed at making molecules sensors of blackbody radiation. And these we're pursuing laser cooling magnesium fluoride as the molecule of choice for sensing blackbody radiation.
Thank you.
Last question, blue microphone.
So I have a simple question.
Name and if you're a member.
Oh, my name is Shashwati, and I'm not a member. And thank you for excellent talk. I really enjoyed. Now, the question is, you showed that FP cavity, I mean the Fabry-Perot cavity, etc. Now, the question is, what is the accuracy of measurement here? And because, you know, when you look at the, say, glass catalog, it has maybe 4 places of decimal. I see the refractive indexes measured in that precision. So in your case, because you're going to all this extreme vacuum, etc., what is the accuracy that you need, and what is the accuracy you can get from this Fabry-Perot cavity?
Yeah, excellent question. So the level, I'm going to change slightly your vocabulary. So the level of precision that you need in your frequency measurement, or more accurately, your frequency difference measurement, sets the lower pressure the lower pressure limit that you can measure. And so in the lab, we use 1550 nanometer lasers. I forget off the top of my head what that is in terahertz, but it's roughly like 10 to the 4 hertz, right? It's 100 terahertz. And we can measure difference, we can stabilize the laser frequency to about 100 hertz on that cavity. So we can really get these lasers to be very, very precise, narrow resonant objects. And with that, we can measure 100 hertz differences between the two cavities. That gets us, we hope, down to about 10 to the minus 5 Pascal.
Okay.
So, and that's an incredible feat of optical frequency metrology. So.
Okay, another thing, I think you did mention that it depends on the mirror quality. I understand that.
Yes.
But the thing is, this is partial mirror, right? It's because you have to measure the output, basically.
Yeah, yeah.
So there will be a limit on how much you can go, I mean, in reflectivity.
Yeah, I mean, you can never reach perfect reflectivity, just like you can never reach perfect vacuum. So one of the quantity of choice when you're using free space Fabry-Perot cavities to measure you don't necessarily quote the reflectivity of the mirrors. What you quote is the width of one of those resonance peaks compared to the spacing to the next one. We call that the finesse. That ratio is called the finesse of the cavity. And we started off with finesses, I think, of about 1,000 or 10,000. We've worked our way up to finesses of 10 to the 5. So these are very, very narrow, resonant, highly reflective mirrors. But they're not perfect.
Okay. Another question. That you are using these FP cavities to measure the gaseous material.
Yes.
But can you also use some solid bulk material to measure the refractive index of?
Oh, you mean insert a bulk material into the cavity?
Yes.
In principle, you can. The problem with a bulk material is that most bulk materials will scatter and so ruin the finesse of your cavity. But in principle, you could. And you would get out some piece of information about the bulk material if you were to do this. But let's say I wanted to measure the index of refraction of a piece of glass. I'm probably, just for the sake of simplicity, not going to put it into a Fabry-Perot cavity, but I'll put it into an interferometer. And if I know the thickness of the glass when I dump it into the interferometer, I'd be able to work out what the index of refraction is pretty accurately of the glass.
I'm afraid we need to wrap things up now. So
Thank you.
save
Thank you
it
very
for the
much.
social
Sorry.
hour. So let's thank our speaker. Before you go, we have a few gifts for you, and those include a framed copy of the announcement of your talk, a signed copy of Volume 17, First Edition of the Bulletin of Philosophical Society, in which you'll find the reasons that they formed the organization, who the original founders were, 3 histories, some early minutes paired with later talks on a similar subject like transmission of malaria and preventing malaria disease, and a ribbon of the society with the 3 stripes signifying the symbol for the Henry, in which we discussed earlier. And with that, thank you so much.
Thank you.
Before you go, we have the usual few closing announcements. The next lecture will be the 2,531st meeting on February 20th. The speaker will be Karen Lloyd of USC, and she'll be speaking about intraterrestrials, the strangest life on Earth. These things have an incredibly slow metabolism, and they live for thousands of years. And we didn't know anything about them 15 years ago. The tagline is how organisms that live deep beneath their surface are challenging basic assumptions about the nature of life. On March 6th, Jonathan Coopersmith of Texas A&M will be talking about Robert Goddard and the first flights of a liquid-fueled rocket, because it's the 100th anniversary of that first flight. March 20th, I will be telling you soon who the speaker will be. On April 10th, the speaker will be Amy Mainzer of UCLA, and she'll be talking about planetary defense and the NEO mission. And on April 24th, we have Harris Lewin of ASU, and he'll be talking about the Earth Biogenome Project. This is the whole schedule, with those blanks to be filled in shortly. And you will note that there is one additional speaker we already have, which is Earl Miller, and he'll be talking on the neuroscience of executive function and consciousness. And I think he's going to try and prove that people are actually conscious. No, just kidding. About 10 days in advance of all events, PSW sends all members invitations to the pre-lecture reception and dinner with the speaker, and notices of the lecture itself are sent to everyone on the PSW friends list. So feel free to join PSW if you haven't already. And if you don't want to join but you want to know about the lectures, sign up for the mailing list on the website. You can link to our calendar and automatically have it populate your personal information manager. And with that, let's thank our crew who ran the cameras and ran the microphones and ran the video in the back of the room and set all this equipment up, and we'll break it down and bring it home. And before you go, please return your badges to the bin in the back. Save us a few bucks. And with that, I will now accept a motion to adjourn the 2,530th meeting to this social hour. I have Bob's reliably given us a motion. Frederica's reliably seconding. All members in favor? Aye. All members opposed? The meeting is unanimously adjourned to the social hour.